Okay, so up until this point, we've talked about unsigned binary numbers. So unsigned binary numbers, I've been referring to them just as binary numbers, but they're really unsigned in that they are only positive. So 0 or positive. So again, up until this point, we've only talked about unsigned binary numbers, which are positive numbers. So our ranges have gone from, for example, for 4 bits, 0 to 15. For 5 bits, it would be 0 to 2 to the 5 minus 1. 2 to the 5 is 32, so minus 1 is 31. So I've talked only about positive numbers. Well, what if we want to also deal with negative numbers? So, for example, we have a computer program that's calculating bank deposits or withdrawals. Well, we have to deal with negative numbers there too as well. We call these numbers signed binary numbers. Signed numbers can represent both positive and negative numbers. Well, we're going to have to figure out a way to do this. And two of the most common ways that we do this are using sign magnitude representation or choose complement representation. And in computers, as we'll see in a moment, choose complement representation is really the one that we use. Okay, let's talk about both of these representations for signed binary numbers. Again, signed binary numbers are numbers that can represent both positive and negative values using binary numbers. For signed magnitude numbers, we'll have one sign bit, and then the rest of the bits are used for the magnitude. So if we think of the value minus 9, for example, well, that value has a sign. You can use one bit for the sign, and the rest is the magnitude, the rest of the bits. So in this case, 9, we need at least 4 bits to represent the magnitude and a sign bit. For the sign bit, we use the most significant, or the leftmost bit, most significant bit, MSB. And we use 0 for positive and 1 for negative. So in this case, our sign bit, negative 9, would be 1. And then the magnitude, here's our magnitude, is 9. Well, that's an 8 plus a 1. So this is the sign magnitude representation of minus 9, using the fewest number of bits. We could have used more bits for the magnitude. In that case, let's say we used 8 bits, for example. Well, we'd still have the sign bit. Here's our sign bit. And if you use 8 bits for the magnitude, 1, 2, 3, 4, 5, 6, 7, 8. 1, 0, 0. We still have a 1 in the 8th place and the 1's place, and the rest of them are going to be 0. So let's do another example, a 4-bit sign magnitude representation of plus 6 and minus 6. Well, for plus 6, we're going to put a 0. Number 0 means plus in the sign bit. And then we have the magnitude of 6 using 3 bits. So 4 bits refers to the entire number of bits for the entire representation. So we'll use the remaining bits, 3 bits, for the magnitude, and we'll get 1, 1, 0. Minus 6, very similar, except we just have a different sign. The sign is now 1 to indicate negative, and the magnitude bits are the same. As a side note here, we can also represent these values using hexadecimal as shorthand to represent these bits. So hexadecimal in this case would be the hex digit 6. And in the -6 case, this is the hex value 14, which is E, hex E. What is the range of an n-bit signed magnitude number? Well, let's write it out for 4 bits. Again, use an example and then extrapolate it to the general principle. So for 4 bits, the most positive number is 0, 1, 1, 1. The most positive number is 7. The most negative number is, well, that same magnitude, 7, but now negative. We can go from -7 to 7 for 4 bits. So -7, this is -2 to the 3 minus 1. Most negative value. Most positive value is 2 to the 3 minus 1, or 8 minus 1. So now we can extrapolate for an n-bit signed magnitude number. Well, most negative number is -2 to the n minus 1. Well, this was 4 bits, and we had a 3 here. Minus 2 to the n minus 1 minus 1 to 2 to the n minus 1 minus 1. And again, written out nicely for your convenience. But again, if you don't remember what the range of an n-bit signed magnitude number is, do an example. A simple but non-trivial example. So for example, 4 bits or 3 bits. And we can also write it out in mathematical form. So for some number, a sub n minus 1 to a sub 0. So in our example we had, let's take, for example, -6, 1, 1, 1, 0. And now we would, this part, from I equals 0 to I equals n minus 2, it's the same as unsigned binary. And that makes sense because that's our magnitude portion. A sub 0 to a sub n minus 2 in this case, a sub 0 to a sub 4 minus 2, a sub 2. Just going to add those together. So 0, a sub 0 times 2 to 0, plus a sub 1 times 2 to the 1, plus a sub 2 times 2 to the 2. So in this case, a sub 0 times 2 to the 0, plus a sub 1 times 2 to the 1, plus a sub 2 times 2 to the 2. We're going to add those together. And then we multiply it by -1 to the power of a sub n minus 1. So that's the sign bit. So here's our sign bit. -1. Then in this case we have the power of 1. So a sub n minus 1. A sub 3 in this case. When n equals 4. So -1 to the power of 1 is just -1. So it negates this entire value. So this value was 4 plus 2, which is 6. And it just negates it. So we get -6 as expected. If instead, like in the other case, the 0, 1, 1, 0 case, we expect to get +6, well, we'd get still, this quantity would be the same, adding up the magnitude bits would still give us 6. But then we'd get -1, that factor in the front would give us -1 to the Well, a sub n minus 1 in this case is 0. Anything to the 0th power is 1. So we'd get 1 times 6. And we just get 6. Okay, so let's review our unsigned binary numbers. We just multiply the bit by its column weight and add them together for I equals 0 to n minus 1. For signed magnitude, we do that addition of the digit, or the bit, binary digit, and the column weight, just for the magnitude portion, so 0 to n minus 2, which is the magnitude bits. And then we multiply that entire summation, the magnitude, by either minus 1, if a sub n minus 1 is 1, or 0. If a sub n minus 1 is 0. And here's another example. We have the value minus magnitude 5. So we add up our magnitude bits. 1 times 2 to the 2, so 1 in the 4's place, plus 1 in the 1's place, we get 5. 4 plus 1, we get 5. And then we raise minus 1 to the sign bit, to the 1 power. So minus 1 to the 1 is minus 1, and we can figure out that our value is minus 5. So, major issue with signed magnitude numbers is that addition doesn't work. So, for example, if we had minus 6 and plus 6, we'd expect to get 0, but if we actually do that, here's minus 6 and plus 6, we get well, let's see, 4-bit addition, 4-bit result. Here's our result right there. Certainly isn't 0, so that's a problem. Addition doesn't work. And we also have 2 representations of 0. So here's negative 0 and plus 0. Well, those are both 0. But now we have 2 representations of it. So our hardware has to deal with, hey, which 0 are you using, minus 0 or plus 0? And we have to consider now multiple representations of 0 instead of just 1. It increases our complexity. So these are 2 major disadvantages of signed magnitude numbers. Addition doesn't work, major problem, and we have to deal with 2 representations of 0. So now let's look at the second way of representing signed numbers, or numbers that can represent both positive and negative numbers. These are 2's complement numbers, and these numbers don't have the same problems as signed magnitude numbers. Addition works, and there's only 1 representation for 0. So 2's complement numbers, again, they can also represent positive and negative numbers, just like our signed magnitude numbers, but in a different way. Before we had, for example, with a 4-bit number, we had our 2 to the 0, 2 to the 1, 2 to the 2, and 2 to the 3's place. This is for unsigned binary. Now for 2's complement, it's similar for these least significant bits. It's exactly the same. 2 to the 0, 2 to the 2, 2 to the 1, 2 to the 2's place. But for our most significant bit, instead of having the weight of 2 to the 3, has the weight of minus 2 to the 3. So the 1's, 2's, and 4's place, just like before, but now in the most significant bit, we have the minus 8's place. So for example, if we had this number, 1, 0, 1, 1, well, we have 1, 1, 1, 2, and 1 minus 8. So the value is -8 plus 2 plus 1 gives us -5. And I'll show another way to find this value. So 2's complement numbers, the most significant bit, the MSB, has the value of -2 to the n minus 1. That helps you feel better. You can do this. -2 to the n minus 1. And so the most positive 4-bit number is, let's see, well, it would have a 0 in that most significant bit for sure, and then the highest value in the remaining bits. So the most positive 4-bit number is 7. The most negative 4-bit number, well, we'd want to put a 1 in that negative position in the -8's place. And we wouldn't want to add any positive numbers to that. We want to keep it the most negative number. So the most negative number we can represent is -8, -2 to the 3. So most significant bit still indicates the sign. That most significant bit's going to be 1 if it's negative, 0 if it's positive. And so that's also a useful thing for us. We can just look at that most significant bit to figure out the sign of the number, even though it's not officially the sign bit. And we can think about the range of an n-bit 2's complement number. Well, the range for the 4-bit number was 7, was the most positive number. So 2 to the 3 minus 1. The most negative number was -2 to the 3. So in general, for an n-bit number, we get 2 to the n minus 1. Right, for 4 bits, we had 2 to the 3, so that was n minus 1, minus 1, to minus 2 to the n minus 1. And again, written out nicely for your convenience. So review, for unsigned binary numbers, again, we just add the digits multiplied by their weights all the way up to the most significant bit, a sub n minus 1. And for 2's complement, we do the same for the least significant bits, so bit 0 to bit n minus 2. And then we add it to the most significant bit times minus 2 to the n minus 1. So in this case, we look at our least significant bits, just add them up as we normally did in binary. In this case, we have a single 4, so we have a 1 4 and a 1 1. We get 5 plus, so this together is 5, plus this most significant bit, 1, times 2 to the minus 2 to the 3. So we get plus a minus 8. So this is the 2's complement representation of minus 3. So 1, 1, 0, 1. If you want to put 2's complement there instead of 2, that's fine. Or we could say it in words. This is the 2's complement representation of minus 3. Okay, now I'm going to show you another way to figure out that this is in fact the 2's complement representation of minus 3. And this is useful for larger bits. So when we have 2's complement numbers with larger numbers of bits. This process is called taking the 2's complement. So this is separate from the 2's complement representation. So the 2's complement representation is what we just talked about. So it can represent both positive and negative numbers. Taking the 2's complement helps us manipulate 2's complement numbers. So this is a process that helps us manipulate 2's complement numbers. So taking a 2's complement flips the sign of a 2's complement number. So it turns a positive 2's complement number into a negative the negative version. So 25 turns that into minus 25 if we take the 2's complement. Or it takes a negative number and turns it into the positive version. So it would take minus 14, turn it into positive 14. This process is as follows. We invert the bits, which is called taking the 1's complement. That process of inverting the bits is called taking the 1's complement. And then we add 1. So to take the 2's complement, we need to do two things: invert the bits and add 1. So let's take, for example, the value 3. So in unsigned binary, it's 0, 0, 1, 1 base 2, and also in 2's complement. So to take the 2's complement, so we want to flip the sign of 3 and turn it into minus 3. We're going to flip the sign of 3 and turn it into minus 3. We're going to do two things. First, we're going to take the 1's complement. So 0, 0, 1, 1. Taking the 1's complement, we'll invert each of the bits. We'll get 1, 1, 0, 0. And I actually like to align these up so it's not, so you don't get off by a bit or miss the alignment. So the first step is to take the 1's complement, invert the bits. Taking the 1's complement means invert the bits. So we take the 1's complement, step 1. And step 2 is to add 1. 1 plus 0 is 1, 0, 1, 1. So 1, 1, 0, 1 is the 2's complement representation of minus 3. So again, taking the 2's complement is a process of flipping the sign of a 2's complement number. So here's another example. We can take the 2's complement of 6. So 0, 1, 1, 0 is the 2's complement representation of plus 6. We want to figure out how you represent minus 6 in 2's complement. Well, I can take the 2's complement to flip the sign. So I invert the bits, step 1. 1, 0, 0, 1. I'm just inverting each of those bits. And step 2 is to add 1. 1 plus 1 is 2. 0 carry the 1. 1, 0, 1. So this is the 2's complement representation of minus 6. We've now flipped the sign of the original number. And there it is written out for your convenience. So if I want to represent some value in 2's complement, if it's a negative value, I can start by first, so let's say we wanted to represent the value minus 14, for example, in 2's complement. I can start first by representing just the magnitude. (14) in 2's complement. Well, let's see. 1, 2, 4, 8 doesn't have a 16 in it. It has an 8. 14 minus 8 is 6. So I'm going to get a 4 and a 2. I'm doing that quickly, but I would recommend writing it out by hand. So we have 14. Is that the 2's complement representation of 14? Well, it can't be because there's a 1 in the most significant bit. So that would be some negative value. So in order to make that the 2's complement representation of 14, I need to put an extra bit here, a 0 Now that's the 2's complement representation of 14. This is one of the most common errors in using 2's complement numbers. Okay, so again, the goal is to write minus 14 in 2's complement. I'm not there yet. First I represented plus 14, so just the magnitude. And now, step 2 is to take the 2's complement. Of 14. That process of allowing me to flip the sign of plus 14 to turn it into the 2's complement representation of minus 14. So again, invert the bits. We get 1, 0, 0, 0, 1. Step 2 is to add 1. 1 plus 1 is 2, 0, carry the 1. Get a 1, 0, 0, 1. So the 2's complement representation of minus 14 is this. This is minus 14 in 2's complement. We can also use 2's complement to figure out what the decimal value of a 2's complement number is. So if we have this 2's complement number, again, if it's more useful to you, you can put that 2's complement, but we've already said it in words. So 1001 is a 2's complement number. We could do the thing where we say 1 plus, well, no 2, no 4, and a minus 8. So minus 8 plus 1, we're going to get minus 7. But again, we can use taking the 2's complement to figure out the magnitude. We already know it's negative because it has a 1 in the most significant bit. So we know it's negative. Now we just need to figure out the magnitude. So we know it's negative something. We need to figure out what that something is. We can do that by taking the 2's complement. We're going to invert the bits, step 1. So 0, 1, 1, 0, and add 1. You get 1, 1, 1, 0. As expected, the magnitude is 7. And so we already knew it was negative, and we now can plug in the magnitude. So 1001 is the 2's complement representation of minus 7. And here we have it written out for your convenience. So I've shown you 2 ways of figuring out what a 2's complement number is. Taking the 2's complement, the method I showed you second, is the recommended way of figuring out the value of a negative 2's complement number. Okay, so as a review, we have both signed magnitude numbers and 2's complement numbers as representations for signed binary numbers, which means binary numbers that can represent both positive and negative numbers. Remember that the process of taking the 2's complement is a process of manipulating 2's complement numbers. It helps in both writing 2's complement numbers and deciphering them. So let's look at 2's complement addition. I claimed that it just worked and it gave the correct result. Let's take a look at that. So we're going to add 6 and minus 6. So you can take the 2's complement of that number. We already did, but we'll do it again. 2's complement, taking the 2's complement in that process, we'll flip the sign. I know it's a negative number already because it has a 1 in the most significant bit. So I just want to figure out the magnitude. I take the 1's complement, invert the bits, add 1. So this entire process is called taking the 2's complement again. 1 plus 1 is 2. 1, 1, 0. So in fact, the magnitude is 6. I knew it was negative. So that's minus 6. And I know the top number is 2 plus 4 is 6. 2 plus 4. The 1 in the 2's place and the 1 in the 4's place. 6 minus 6. Sure hope to get 0. Let's see what happens. 0 plus 0, 0. So far, so good. 1 plus 1 is 2. 0, carry the 1. 1 plus 1 plus 0 is 2. Again, least significant bit is going to be 0, carry the 1. 1 plus 0 plus 1. Again, 2. 0, carry the 1. Okay, what happened here? What's the result? We have 4-bit operands, and so we get 4-bit results. The result is just these 4 bits. Addition never includes that 5th bit. 4-bit addition, 4-bit result. So with 4-bit addition, we're never, even in unsigned binary, we're never going to use that 5th bit. It'll, again, 4-bit addition, 4-bit result. N-bit addition, N-bit result. And so the result here is, in fact, 0. But what's going on with that? Is that a carry out? What's going on with that extra 1 here? That 5th column that was a 1. Does it mean overflow? In 2's complement, it doesn't. In 2's complement, this does not indicate overflow. Only in unsigned binary does that indicate overflow. That 1 carry out of the most significant column does not indicate overflow in 2's complement addition. It only indicates overflow in unsigned binary addition. So again, 4-bit addition, 4-bit result. 6 minus 6 in fact results in 0. Let's try another one. Minus 2 plus 3 using 2's complement numbers. We can double check that this is in fact minus 2 is 0, 0, 0, 1 plus 1. I'm just taking a 2's complement of that. Invert the bits, add 1, and I in fact get 2, so I know the magnitude is 2. I know it's a negative number, and so this is in fact minus 2, and this is 3. Expecting to get 1 here. Minus 2 plus 3. Hoping to get 1, let's see what happens. 0 plus 1 is 1. 1 plus 1 is 2. 0, carry the 1. 1 plus 1 plus 0 is 2, which is 0, carry the 1. 1 plus 1 plus 0 is again 2. 0, carry the 1. 4-bit addition, 4-bit result. Here is my result. So again, here typed out for your convenience as well. We show that 6 plus minus 6 gives us, in fact, 0. Remember, 4-bit addition, 4-bit result. Discard the carry out bits. And minus 2 plus 3, another example, gives us, as expected, 1. Again, 4-bit addition, 4-bit result, or in general, n-bit addition, n-bit result. So for 2's complement numbers, addition works, and only one representation of 0. The only way to represent 0 is, well, 0 in the most significant bit for 4 bits, and then 0. So there's the single representation of 0. So how do we increase bit width? So either we want it to have larger numbers, or for example, we're trying to add a 3-bit number to a 5-bit number. Sometimes we need to increase the bit width. Well, how do we extend the numbers from n to m bits? So for example, from 3 to 5 bits, where m is greater than n. Well, there are 2 things we could do: sign extension or 0 extension. Sign extension takes the sign bit and copies it to the most significant bits. Number value ends up being the same. So let's say, for example, we have the sign bit of 0. Well, we'll take that sign bit, if we want to extend it from 4 bits to 8-bit representation, we'll take that sign bit and just put it into the most significant bits. If that sign bit however, is 1, we take it and, again, put it into the most significant bits. Well, clearly, this number is the same if they're 2's complement numbers. And this number down here, well, let's see, what's the value up here? -5, we can double check that. Take the 2's complement, invert the bits, add 1. In fact, we do get 5 there. And I want to check if this is the 2's complement. That's the 8-bit 2's complement representation of -5. Again, we can take the 2's complement, invert the bits, add 1, and in fact, we do get 5 is the magnitude. We know it's negative. So if it's a 2's complement number, sign extension preserves the value of the number. 0 extension, on the other hand, ignores the sign bit and just puts 0 into the most significant bits. So no matter what, it doesn't even look at the sign bit, just pops zeros into the most significant bits. If you want to go from 4 to 8, 4 zeros in the top 4 bits. Again, no matter what the 4-bit value is, puts zeros into the top 4 bits. So if this was a 2's complement number, if it's positive, no problem. The value is preserved. But if it were a negative number, now the value isn't preserved. So the value changes for negative numbers, negative 2's complement numbers. But if in fact this was originally an unsigned binary number, instead of that value being -5, it would be 1 plus 2 plus 8 is 11. It would have been 11 originally, and now the value is preserved. So now let's compare our number systems. So unsigned numbers, which we talked about at the very first, unsigned binary numbers have the range 0 to 2 to the n minus 1. And we can represent, well, 2 to the n values. Signed magnitude numbers can represent, well, minus 2 to the n minus 1, minus 1, to 2 to the n minus 1, minus 1. We actually lose one of the number of values we can represent. So instead of 2 to the n values that we can represent with n bits, we can only represent 2 to the n minus 1 values. Why minus 1? Well, we have 2 representations of 0. So we lose one of the encodings to the redundant value of 0. For 2's complement numbers, we have the range of minus 2 to the n minus 1 to 2 to the n minus 1 minus 1. We can still use all of our representations for unique values and represent 2 to the n values. So if we look at the example for 4 bits, with 4 bits, unsigned binary numbers can go from 0 to 15. For 2's complement, we can only go from 0 to 7 for 4 bits, but we basically take that top part and shift it down to the negative portion of that range and represent from minus 8 to minus 1. For sign magnitude, we have 2 representations of 0, and the values from 0 to 7, and minus 1 to minus 7. So in this module, we've covered a lot of stuff. We covered number systems, decimal, binary, hexadecimal, and then generalized it to really any other base. And we also talked about sign numbers, sign magnitude, and particularly 2's complement numbers. We also talked about how to convert between those different number systems.